All right, so last class, what we did was we just went through the first half of 3.5. So we were looking at this concept of atoms and ions. We said atoms are an uncharged particle or an uncharged element, and that all the elements in our periodic table are atoms. They're represented as atoms, they're not as ions. Ions are different. An ion is a charged atom, okay? The minute an atom gets a positive or negative charge, it goes from being an atom to being an ion. We talked about there being two types of ions, okay? We talked about there being cations and anions. Cations are generally any element that tends to lose an electron or donate an electron to another element in order to become stable, okay? So generally we're talking about our metals. Most of our metals form cations, and cations are positively charged. So that means that most of our metals have a positive charge. And we know this because if we look at metals like, for example, lithium, that's got a positive 1 charge. If we look at metals like magnesium, that's got a positive 2 charge. Okay, we know this, and we know that based on the valency that these are cations. Okay, so whether an element or whether an atom becomes a cation or anion is dependent on whether there is a loss of electrons or whether there is a gaining of electrons. Remember, we said that electrons are negatively charged, yeah? So when we're talking about protons, they're positively charged, but our electrons are negatively charged. So anions generally are our non-metals that we learned about. So are like halogens, our noble gases, all of those are non-metals, and all of those form anions. That's because, for example, when sodium, which is a metal, donates or gives away its last electron in that outermost shell to something like chlorine, which is a non-metal, actually becomes more negative, okay? Because when you're gaining an electron, you're gaining more negativity. So overall, that chlorine atom becomes chloride, okay? The name changes, and it also becomes more negative in the process, leading to it becoming an anion, okay? In the same process, what happens is that sorry, let me just admit these people. Okay, in the same process, what happens is because sodium has now lost that electron, it becomes less negative. That is, it becomes more positive. And that's why we say cations and metals such as sodium actually form cations or positively charged particles there, okay? So that's basically how anions and cations form. And we basically just went through a few examples of this last class. And we just talked about the fact that we can draw this or represent this as a diagram, talking about the 1 electron there moving from the atom to form the cation of potassium there. Okay, so we can draw this or represent this as an electron transfer diagram. And yeah, that's just another example there. And just before we wrapped up last class, what we went through was the charges of the periodic table. And we talked about the fact that according to the group that an element is in, it has a specific valency or a specific charge. Okay, that valency is actually determined by the number of electrons in the valence shell, or the number of valence electrons. Okay, so let me just write that down. And if any part of this doesn't make sense, just let me know which specific part is confusing and I'll repeat it again. Okay, so because we really need to understand this valence electrons and charges thing in order to get the rest of today. So the number of valence electrons determines most of the valencies of the groups in our periodic table. So for example, we know that all group 1 metals or group 1 elements have 1 valence electron in the outermost shell. Remember, we talked about this. So group 1 has 1 electron in the last shell, okay, the shell that's furthest away from the nucleus. And because all of these are metals, and because they tend to lose that 1 electron, as we saw in the case of sodium, for example, in the previous slide, when I drew that up, they tend to lose that electron. When they lose the electron, they become less negative and thus more positive. So that's going to be a +1 charge. The same goes for group 2. That's going to be a +2 charge because beryllium, magnesium, calcium, they all have 2 electrons in the outermost shell, and they tend to lose those electrons. It's easier for those group 2 metals to lose the 2 electrons than it is for them to gain 6 electrons to become stable. Because remember, we said that we need 8 electrons to be stable. So it's easier for these group 2 metals to lose the 2 than to gain another 6 more to make 8 there. Okay, I know it's a little bit confusing, but you just have to keep remembering how many valence electrons we're dealing with in those groups and think about, is it easier for them to lose or gain? With the case of metals, it's always easier for them to lose the electrons they have, okay, because they have so little. So that's for the two valency charges for our group 1 and group 2. For the others, for group 8, we said they're the noble gases. Remember, we said they're noble. They don't mix with the common elements. They don't need anyone to feel complete. They are complete as they are. So they don't really need another element to complete themselves. They've already got 8 electrons in the outermost shell, except for helium. Helium's got 2, but having 2 electrons in the first shell is still a full shell, which makes it stable anyway. Okay, so all of these, because they've got a full or complete valence shell. Sorry, I can't write really properly with this. Okay, because they've got a full or complete valence shell, that means that the noble gases are stable. Okay, if you're stable, you're not losing or gaining electrons, you're just remaining as you are. And for that reason, we say our noble gases have a valency of 0. Okay, with the halogens, we know generally what happens to them is that they gain an electron. Remember, we said sodium, for example, gives the electron to chlorine. So in other words, chlorine is getting an electron. Okay, it's gaining an electron. So that's why that's a -1. Okay, and oxygen, sulfur, selenium, tellurium, polonium, all of those are going to be -2 because they tend to gain 2 electrons there. All right. So, okay, when we're talking about how do the elements give and take electrons from each other, that happens through a process called electrostatic forces. So when you've got a positively charged element like sodium, and we're going to learn about this in the next few slides, and then you've got chlorine, the positive charge of this and the negative charge of chlorine actually attract one another, okay? Because they're oppositely charged. So they attract one another and they're kind of like veer towards one another, okay? And they form a bond, and we call that bond an ionic bond. So we'll talk a little bit more about that in the next few slides. That is kind of the basis of what we're doing today. As long as you understand the charges and you understand the main charges I talked about now, that's really all you need to know. In the SAC, generally, we give you a valency table. So if there's any elements like iron or copper that don't have a set charge, we'll tell you the name, we'll tell you the number or the charge associated with that, okay? So as long as you understand what the charges are for now, you should be okay. Now, if we move on to the next slide, and this is where we're talking about writing the formulas and writing the names of the compounds. I'm just going to tell you the basic idea behind this so you understand why the next few formulas we're going to look at are the way that they are. Generally, when we're writing formulas and we're combining two things, we have to look at the charges, because the charges that those two elements have will determine the kind of chemical formula that they will represent. Okay, so with lithium and chlorine, if you look into your periodic table, can anyone put in the chat box if you've got it in front of you, and just to see how much you guys remember, what's the charge for lithium? What did we say? According to the periodic table, what's the charge, the numerical charge or the valency for lithium? Yeah, excellent. So your lithium charge is +1. Yeah, so we're at +1. We generally don't write +1. I talked about this last class, but for now, I'm just going to write +1. Okay. Chlorine. Can anyone check what's the charge for chlorine? Yeah, -1. Excellent. So -1. Now, what you see here is generally when we write the name of the formula, we have to do this thing called switching charges. We have to basically ensure that the net charge is 0. What that generally means is the number here is given to the corresponding element, and then the number for this element or the valency of this element goes to that element. That's what we call a swap, okay? There's switching or swapping charges. In this case, this is +1 and this is -1. So literally it'll cancel out. So all you have to write is LiCl. Okay, you could also write Li1Cl1, but obviously it's going to be the same thing. We don't write ones anyway when we write charges. Okay, so we only write LiCl. So that's going to be LiCl. Okay, all we're doing is swapping the charge. That was a really easy example because both of the charges were -1 and +1. What about the next one? Let's use that same idea of switching charges. So if we've got Li, we already know Li is +1 from the previous example. This already has the charge attached to it. This is actually called sulfide. Sulfide is a polyatomic anion. Sulfide has S2 minus, okay? We've already been given the charge. How would you write this if you were to swap the charges around? So we want the Li to have the 2 charge and we want the S to have the 1 charge. How would we write that out? If you have an idea, write it in the chat box. Okay, so like I said, all we're doing is we're switching the numbers around. Okay, so this is going to become Li, and it's no longer going to have a +1 charge. It's going to take on this, but we're not going to write 2 minus. We're just going to keep it as 2, like that. S is going to have the +1 charge there. So we're just going to write S. We're not going to write 1 because we generally don't represent 1 like that. We just leave it as S. If it's S like that, I know that that means S1. So then if I just rub out that little 1 there, that's the correct answer there. Okay, that is the formula for the compound that forms when lithium and sulfide come together. Yes, so the 2 was negative, but really, really important rule, guys, when you're writing your chemical symbols, what am I doing? I need to get where's my texter? Okay, when you're writing your chemical symbols, you can't write something like this. This is wrong. Whenever you're balancing equations or writing chemical symbols, the charges have to drop. And basically, that's why we say the rule is that the charge has to be net, a net 0 charge. Okay, that's what I did when I basically put a 2 here. Remember, it started as -2. When I put it as a +2 here and dropped the charge, +2, -2 equals to 0. So that charge is kind of cancelled out. Okay, generally, automatically, when you swap the charges around, the net charge will equal to 0. So then you don't have any charges in your final formula. So that's our final answer, and that is correct. Okay, it's just about swapping charges. Now, I'm going to get you guys to do the next example. So I'll write it out, and then I want you guys to, in the chat box, write down what you think the answer is. So we've got Mg2 plus, and we've got Br minus. Now, Br minus means -1. Okay, minus means -1. Now, swap the charges, and if you've got the answer already, write it in the chat box and tell me what it is. Yep, so far I have some good answers in there. I know it's hard to use subscripts in Zoom chat, so that's okay. I know what you mean. Okay, so yeah, it'll be Mg. Now, Mg will take on the -1 charge of Br, but it won't be negative. It's obviously, we drop the charge, so it's just going to be 1. I'll put an imaginary 1 there for your understanding now, but we have to rub that out later on. Now, with Br is going to take on the charge, or bromine, sorry, is going to take on the charge of magnesium, which in this case is +2, but we don't put a positive, we just put the number. So 2. So the correct answer, after rubbing out the imaginary 1 subscript there, should be MgBr2. Okay, all we've done is bromine has taken on the 2 charge of magnesium. Magnesium has taken on the 1 charge of bromine. So they've just swapped the charges. That's about it. Okay, and then that would be the correct answer there. Okay, they've just literally swapped the charges, swapped the numbers, I mean. The charges, we don't write the charges. We've just swapped the numbers of those charges, and they become what we call as a subscript. Okay, these are things that we're going to learn a lot more when we start chapter 4, when we write chemical equations, but we do need to understand the basics. Yeah, we never write the charges. Yeah, we never, ever, ever write the charges in a chemical equation or in a chemical formula. Yeah, we always drop the charges. One thing to remember, guys, as well is I'll write 2 things now, and I'll tell you that how these 2 are different. If you know the answer to this, okay, I'm going to write 2, and I want you to tell me which one is correct. Okay. Although these look similar, so let's say this is chemical formula of student 1 that they wrote in the test. This is chemical formula 2. If 2 students wrote this on the test, the correct answer would be student number 2, not student number 1. Student number 1 would get this wrong. The answer, or the reason being, is that they've put the subscript in the wrong place. This is a subscript, okay? This is where the subscript goes. It always goes at the bottom. And the subscript tells us the number of atoms of that particular element in that compound. So magnesium bromide in this case is made up of 2 bromide atoms and 1 magnesium atom. Okay, that's what makes up the compound of magnesium bromide. This is wrong because the subscript never goes at the top. It always goes at the bottom. Okay, this is wrong because we only put the charges at the top, not the subscript. The number of atoms or the subscript always goes at the bottom. The charges are the only ones that go at the top. Okay, I know that's a bit confusing, but we are going to do more about this in 4.1 when we start chemical equations. But just for your understanding, so you understand the next few formulas that we're looking at, the subscript, again, the one at the bottom tells us the number of atoms that are in that element or in that compound there. Okay, I want you guys to try the next one. I'm rubbing all the scribbles off. I want you all to do D now, Al3 plus and O2 minus. So we've got aluminium, 3 plus, and then you've got oxygen, which has a 2 minus charge. We know that, we wrote that in our periodic table. Swap the charges, do the old swapperoo, switcheroo, whatever you want to call it, and swap the charges. And make sure you're only focusing on the number. You're not bringing down any of those plus or minus, just the number. So swap the number for each of those and write down the chemical formula. And if you've written it down and you want to let me know, write it in the chat box and I can have a look. Yep, excellent. Good work. Some good answers so far. Okay, so all we're doing, guys, is writing Al. Now, aluminium is not going to retain its 3 plus charge. It's going to swap. Remember, it's going to take on the charge of oxygen here. So Al2, but we don't put the 2 at the top. We don't write this. This is wrong. Okay, so what we're going to do now is we are going to put the superscript at the bottom. We call it a subscript. So we're going to put that at the bottom here. Let me put it in a different color so it's clearer for us to see. So Al, that's a 2. That's the 2 from oxygen, remember? Go back to our red. Oxygen. Now, oxygen is going to take on the charge of aluminium here, which is 3. Okay, but we're not going to put the plus or minus sign, just the number. All right, so what we're going to do is, let me go back to my color green. Okay, O3. So that is our chemical formula for when aluminium and oxygen form together. And the name of this compound is aluminium oxide. Okay, it's called oxide and not aluminium oxygen. Can anyone give me a reason if you understand this? Why is it called aluminium oxide rather than aluminium oxygen? Why oxide? And I'll give you a clue. The same rule applies for chlorine. When chlorine turns into something, it also becomes chloride. Yep, because it's a compound and not just 2 elements. That's correct. Yeah, so when oxygen goes from being a single element to forming into an ionic compound, which is when it interacts with a metal, the name of it changes. This is the same concept we used to explain sodium chloride, okay? It's the same reason why we say sodium chloride rather than sodium chlorine, okay? Chlorine is the name of the single element. Chloride is the name of the anion formed when chlorine interacts with sodium, okay? In the same way, oxide is the name of the anion formed when oxygen interacts with aluminium, as we see in this example here. Okay, so the last one, I want you guys to give that a go. So look at the calcium and the oxygen and just write down in the chat what answers you guys would get for that. So I'll just write this down for you guys to see that clearly. Okay, what are we going to get there? Write it in the chat box using the correct chemical formula. Okay, so the same formula, the same concept as we did for part A, when the charges are the same, what happens? The charges cancel out. So you won't be writing this, Ca2O2, this is wrong. Okay, this is wrong because when we try to swap the charges or swap the numbers here, they actually automatically cancel one another out, okay? Because 2 plus or 2 minus 2 is 0. So what you're going to write here is actually, let me just rub this out. Last one's not going. Okay, never mind. Let me just scribble. Okay, the last, sorry, this should be Ca1O1. Okay, so technically it should be CaO, calcium oxide, because those two charges will cancel each other out. So 2 minus 2 means the net charge will be 0. So that means you don't need to change the subscript there. There'll be an equal number of calcium and an equal number of oxygen atoms. So in calcium oxide, which is the name of the substance formed here, or the name of the compound that's formed, calcium oxide will have 1 calcium atom and 1 oxygen atom. Okay, is there anything so far with this that doesn't make sense? And like I said, we're just starting this now. We are going to do more of this in the next chapter as well when we do chemical equations. But do you guys kind of get the basic idea of swapping charges and understanding how the number of atoms can change there? Yes. So the oxide thing basically means when you've got oxygen, okay, by itself in the periodic table, oxygen is called oxygen, right? It's an oxygen atom. It doesn't really change, okay? But when oxygen goes from being in the periodic table as a single element to actually forming an anion, because oxygen is a nonmetal, it always forms an anion, it actually becomes called oxide. It's no longer called oxygen. Okay, in the same way that chlorine, for example, in the periodic table, chlorine is also a nonmetal, okay? By itself, as a single element in the periodic table, it's an atom. It doesn't have a charge. But when chlorine combines with a metal like sodium or lithium, it actually becomes, again, an anion. Okay, chlorine becomes an anion. And when chlorine becomes an anion, the name of chlorine changes to include the IDE or "ide" suffix, which is chloride. Okay? And the same thing can be applied to any of those nonmetals there. So fluorine, for example, becomes fluoride with an IDE. Bromine becomes bromide with an IDE. Okay, iodine becomes iodide with an IDE. So this is just the name change that occurs when these single elements go from being atoms that are uncharged to actually developing a negative charge and becoming an anion. Okay, alrighty. I hope that makes a little bit more sense. So we'll just keep moving on now. And the reason we did this activity today is I want you to understand what this is now. Sodium chloride, okay? We already know, I've done this a million times in class and in the Zoom. We know what the electron transfer diagram for this is. Now, in order for you to understand the formula that's in purple there, that's why we were working on that question before, okay, with the formulas and with the chemical formulas and looking at the number of atoms. Because we know that when we draw the chemical formula for NaCl minus, we know that when we do the swapping of charges, it's just going to be NaCl. Okay, there's no numbers there, so there's not going to be a random 3 coming out of nowhere. That's not going to happen. Okay, we know that it's only going to be NaCl. And so that's why these two elements, when Na and Cl get together, that's why we have this chemical formula coming up. Okay, that's the first thing we need to understand. Second thing we need to understand is this tells us that there is 1 sodium atom and 1 chlorine or chloride atom there, okay? 1 of each. How we know this is that NaCl, there's no numbers at the bottom, okay? There's no numbers like 3 or 2 here, okay? If there was, then that would mean there's 3 sodium atoms and 3 chlorine atoms, but there isn't. It's just NaCl by itself. So that's why, as you can clearly see here, we have 1 sodium atom and 1 chlorine atom, okay? This is not the case for the next few examples we're going to look at. But so far, does this make sense? That when you read a chemical formula like NaCl, that means there's 1 atom of sodium and 1 atom of chlorine. If that doesn't make sense, just let me know. I'll explain it again. Okay, if it doesn't make sense anyway as we're going through, just let me know at any point and I can explain that again. Okay, yeah. So basically when we write NaCl, NaCl means you've got 1 atom of sodium and 1 atom of chlorine, okay? If we were, now this is not the correct formula, but just hypothetically for the purpose of an example, if NaCl's formula was something like this, which it's not, but let's say for the purpose of the example it is, this would mean that there's 2 sodium atoms and 3 chlorine atoms, okay? The number that's underneath the name of the element in a compound, which is what we call as the subscript, is the number of atoms that is contained of that element within the compound, okay? So here we see 1 electron shell diagram for representing the sodium atom, 1, and 1 electron shell diagram representing the chlorine atom, 1, okay? And that is consistent with our formula, which is NaCl. Remember I said we never write 1 in chemistry with the compounds. We always just assume it's there, but we don't technically write Na1Cl1 like that, okay? But this formula is proving to us or supporting this idea that there is 1 of each element or 1 of each atom in that compound there, okay? Because sodium chloride is a compound. When you mix a metal with a non-metal, it becomes a compound, okay? In this case, it's an ionic compound, and we call ionic compounds ionic because they involve the transfer of ions, okay? And this is a non-metal. Okay, so that's what we call as an electron transfer diagram. And we drew this in class. We said that one last lucky atom that's in sodium in the outermost shell is transferred or donated or given away to chlorine, who needs that atom. Because remember, chlorine has 1, 2, 3, 4, 5, 6, 7 electrons in its outermost shell. And we need 8 electrons in order to ensure a stable atom. So sodium donates the 1 electron to chlorine to make it 7, plus 1 equals to 8 electrons. Okay, that's the basic idea there. Okay, so moving on now, magnesium chloride. Now, I know the formula is already given to you, but just to reiterate, just for you to understand, how is it MgCl2? Now, can anyone tell me the formula of magnesium? Not formula, sorry, the valency or the charge that magnesium is given? You can look into your periodic table and see the valency there for the group that magnesium is in. Just tell me the number, and then I can see how much you guys are understanding. Yeah, 2, excellent. So we know Mg is in group, magnesium is in group 2, so it's got a 2+ charge. Chlorine is 1 of our halogens, so it obviously has a -1 charge. So that's how it works. Now, when we do the swapperoo or the little switching of charges, it's going to, Mg is going to take the charge of chlorine, which is -1, but we don't write -1 here. We can put an imaginary 1 there, but we'll rub it out later. And then Cl is going to take the charge or the number of magnesium, which in this case is 2. So that'll be MgCl2. Now we just rub out that 1 there because it's not really necessary to write 1 subscript. Okay, and that's why the formula is MgCl2. Now, before I show you the electron transfer diagram, can we all, or can some of us in the chat box, whoever gets it so far and whoever can tell me, how many atoms of magnesium and chloride are going to be in the compound of magnesium chloride? So just write magnesium, how many atoms? Chlorine, how many atoms? You can tell that just by looking at the formula, but just write it down in the chat box so I know that you understand. Okay, good. So some of you are saying that, yep, 2 chlorine atoms and 1 magnesium. That's correct. So if I show you guys the diagram now, that's why in this diagram, we've got only 1 magnesium, 1, and we've got 1, 2 chlorine, okay? Because that means 2 chlorine atoms and 1 magnesium atom. Okay, that's the basic idea. That's why when we draw this out, the 2 of magnesium, the 2 outermost electrons or valence electrons that magnesium has, doesn't just go to 1 chlorine. It can't, okay? Because the formula is MgCl2. There has to be 2 atoms of chlorine in this electron shell diagram drawing. In order to do that, what we do is we say one of the electrons goes to 1 chlorine atom and the other electron goes to the other chlorine atom. okay? And that will then make it consistent that our electron shell diagram does reflect the formula for magnesium chloride there. Okay, let's keep moving on. Hopefully you guys understand it so far. These are just some basic examples. Okay, sodium oxide. So now if we talk about sodium oxide and the formula, just so you guys understand how that formula came to be. Can anyone just quickly tell me the charge of sodium from the periodic table? I really want you guys to keep looking into your periodic table. That's why I'm asking you each time. So tell me the formula based on where sodium is in the periodic table, the valency, sorry, the charge. Is it +2, +3? What is it? +1. Okay, it's +1. So we're at plus, we can put a 1 there if you like. Okay, and then oxygen is obviously, whoops, turn this off. Okay, oxygen is 2-. Yeah, we wrote this in our periodic table when I told you to write it down last class. This is what oxygen has. It's a 2- charge. If we swap those charges, what we get is Na takes on the number associated with the charge of oxygen, which is 2. And the 2 goes at the bottom, never at the top. And oxygen takes on the number of sodium, which in this case is +1. Now, remember, we don't really write +1. If you want, just to make it clear, I can write the +1 there. But before we write our final answer, we should always kind of rub it out, okay? So that's why it's Na20, and that's the formula. Now, I want you guys to tell me, using this formula or using this chemical formula we've got here for sodium oxide, can anyone tell me in the chat, how many atoms of sodium are we going to have and how many atoms of oxygen are we going to have? Yeah, okay, good. So yeah, we've got 2 for sodium, so 2 sodium atoms, and we've got 1 oxygen atom, okay? So it should look something like this, okay? So we've got 2 sodium atoms. Now, obviously, because oxygen has a -2 charge, what that means is that it needs to gain 2 electrons. So that means it's already got 6 electrons in the outermost shell. Okay, we've got, 1, 2, 3, 4, 5, 6, yeah? So basically, those 2 sodium atoms, each of which have 1 electron, donate each of those 1 electrons to sodium. So you got +1 makes it 7, +1 makes it 8, and now sodium is stable with 8 electrons in its outermost shell. So, oxygen is stable with 8 electrons in its outermost shell, and sodium, because it's lost each of those 1 electrons, it loses that entire shell and now has 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So each of these sodium atoms now have 8 electrons in their outermost shell after losing that other shell that had the 1. Okay, so now everything is stable. Okay, and this is again an ionic compound. Ionic compound means we've got a metal plus a non-metal forming together or combining together and interacting, and there's an exchange of electrons there. Okay, in this case, sodium has lost 1 electron from each of those 2 sodium atoms and have donated those electrons to oxygen. Okay, and in that process, oxygen has gained the 2 electrons from each of those 2 sodium atoms. Does that make sense so far? Do you guys see how that exchange is happening using those 2 diagrams there? If we give you a formula, even if we give you a formula like Na20, and we ask you to draw an electron shell diagram for this, the main reason I'm going through this number of atoms business is because I want you to be able to be confident that when you are asked to draw up an electron transfer diagram for this formula, you should know in your brain that I will have to have 1 oxygen atom and 2 sodium atoms. So you already know, and you've already mapped it in your brain, that that's what it's going to look like. Okay, so you don't have to worry about how you're going to start it off. Okay, that's basically the idea. So remember, the subscript or the bottom number in a chemical formula tells you the number of atoms. Okay, just remember that. That will be important for you literally for the rest of this whole semester, because how you draw up diagrams, how you write your chemical formulas, all that stuff really depends upon knowing what the number of atoms are and knowing what the subscript represents. Okay, I'm assuming you guys kind of understand it because I don't really see any questions. So yeah, I'm just going to move on. And I've already talked about what ionic compounds are. Ionic compounds are just basically compounds that are formed when a metal, such as lithium or sodium, magnesium, calcium, whatever you want to call it, bonds to a nonmetal like oxygen, carbon, any of those, okay, fluorine, whatever. Okay, whenever you've got a metal bonding or combining or interacting with a nonmetal, an ionic compound is formed. Just remember that, okay? Ionic compound is metal plus nonmetal. That's the formula. That's the basic idea. Okay, now compounds that are held together by ionic bonds are called ionic compounds. Remember before I was saying that the opposite charges make them attract. Okay, with ionic compounds, the fact that sodium has a positive charge here, for example, and chlorine has a negative charge, actually causes there to be an electrostatic charge between the two that cause them to actually veer and travel towards one another and attract strongly rather than repelling and moving away from each other. Okay, that's what we call as the strong electrostatic force. Okay, and that's why sodium is just like, just take it, please, just take the electron, and gives it to chlorine because of those electrostatic forces that are moving sodium so much closer to chlorine and vice versa. Okay, now this idea of opposites attract, of the positive charge of a metal, getting attracted to the negative charge of a non-metal is called ionic bonding. Okay, and ionic bonding is only possible through the electrostatic forces that basically lead to opposites attract, to the positive charge attracting to the negative charge and vice versa. Anything on this slide that doesn't make sense about ionic compounds? Okay. If you guys have questions, you must let me know because otherwise I can't really read your mind, okay? So that's basically what ionic compounds are. Some properties of ionic compounds, just like we've been looking at properties of metals and nonmetals. Remember, ionic compounds are literally a combination of a metal and a nonmetal, right? So they do form some properties that we see in both metals and nonmetals. For example, ionic compounds have high melting and boiling points. Ionic compounds, similar to some metals, are actually hard, okay? But at the same time, they're also quite brittle, all right? Solutions of ionic and what that means, guys, is ionic compounds like salt, for example. If you take salt flakes or salt crystals in your hand, like rock salt, it feels hard, but if I'm to take a hammer or something and smash it, it will break apart. That's what brittle means. It's easy to break, but it feels hard when you've got it in your hand. Solutions of ionic compounds and melted ionic compounds do conduct electricity, but the solid materials do not. So when we're talking about the solutions means that we mix it in water, okay? But the actual solid materials like the solid salt, for example, will not conduct electricity. A lot of our ionic compounds form crystals, okay? So for example, we know that table salt, which is our most well-known ionic compound, forms crystals, okay? We've got salt crystals, you can see that clearly. So yeah, those are some properties of ionic compounds. So maybe just know at least 3 properties from this slide, any 3, but just understand that ionic compounds are a combination of metals and non-metals. So they will share some properties with either metals and non-metals there. Okay, this kind of information, very high melting point, 801 degrees, you don't need to know these numbers, but just understand that this is an example of some of the properties reflected in the text here. Okay, polyatomic ions. Now, polyatomic ions basically are ions that are formed by 2 or more atoms, okay? So for example, hydroxide is a polyatomic ion that's formed when oxygen, 1 atom of oxygen and 1 atom of hydrogen combine together. And that little minus sign or that little negative sign there shows you that the entire compound of hydroxide, which is formed by oxygen and hydrogen, has a minus charge, okay, or has a -1 charge. These are set charges. These are set for the polyatomic ions. These don't change, and they apply to the whole thing. So if we talk about phosphate here, we've got P, 1 phosphorus, we've got 4 oxygen because of the little 4 at the bottom. Remember, we said that's the number of atoms. And the whole thing, the whole ion has a -3 charge, okay? Now, polyatomic ions are different from the single ions we've been looking at. Okay, so Na plus, for example, is a sodium cation. That's the symbol for a sodium cation. Yeah, if we ever ask you to write down the symbol for a sodium ion or a sodium cation, that's what you would write. That's single. That hasn't mixed with anything. That hasn't combined. That's not a compound. It's still an ion. It's still a single thing. This is different from that. Okay, these two are different because this is a polyatomic ion. Now, does anyone know what the word poly means? Poly means more than one, okay? It means many, okay? We see the word poly in many things like polygon, polygamy, okay? Polygamy means you marry more than one person, okay? Polygamy means many, so more than one. Now, a polyatomic ion is basically when you've got more than one element kind of forming a compound. So you've got one atom of phosphorus here, you've got 4 atoms of oxygen, and that when those combine, they actually form a charge that is neither the charge of oxygen nor the charge of phosphorus. That whole compound develops a new charge, which is 3 minus. The good news is we always give you the formulas for these in the test. So you don't have to memorize these, but it's just for you to understand, okay? You don't need to know how to draw these compounds, but you need to understand that, for example, in ammonium, okay, ammonium is NH4 plus. NH4, and it's got a positive sign, okay? Ammonium is NH4, meaning it's got 1 nitrogen atom, 4 hydrogen atoms, and the whole compound has a positive 1 charge, which means that it forms a cation, okay? That's the basic idea, and that's literally what I talk about here as well. All right, so that's the basic idea behind the polyatomic ions. They're literally ions that form from more than one element. Okay, rather than a single element, we've got more than one that combines. And these have their own specific charges, which are given here and which will be given to you in any test situation. Okay, that's always there in your data booklet. Okay, so that's literally polyatomic ions. This just gives you an example of a polyatomic ion, which is calcium carbonate. Again, not something really important, but just as an example there for you. All right. Ionic bonding model just tells you that obviously metals tend to lose the electrons and they become positively charged, whereas non-metals tend to gain. This is literally just what we went through in the beginning of the PowerPoint at the beginning of 3.5, just showing that we can represent this idea in a visual form by drawing a diagram like this, where the purple ones would represent a metal and the green ones would represent a non-metal. And those little sticks in between, the white sticks that look like lollipop sticks, those are actually just the electrostatic forces of attraction that bond these metal ions with the non-metal ions. Okay, so this is just a visual model. There's literally nothing new in terms of content on this slide, so don't stress. Again, just giving you a more clearer picture of what that visual model looks like. And I've already explained all of this already, so I'm not going to go through this again too much, but yeah, I told you guys what the type of charges are. Metals tend to have a positive charge, non-metals have a negative charge. We talked about the fact, balancing we haven't done yet, so don't stress about this just yet. In fact, I'll put a little cross over it because we haven't done it yet. We're going to do this in chapter 4. We talked about how we write the formulas and we talked about subscripts. Okay, subscripts are the number at the bottom and they tell us the number of each type of ion or atom that's in that equation or in that formula. Okay, so that's the writing of chemical formula rules. And this is literally just what we went through. We already talked about how the IDE comes up and we've already talked about what the polyatomic ions are as well. So this is an example of the table we can give you in a test situation. Again, you don't have to memorize some of the charges, particularly those of your polyatomic ions. We will give you those charges in a test situation, okay? That's the same for anions as well. And yeah, what we'll do is we won't need this for now. What we'll do is probably in the first class before we start 3.6 on Friday, I'll make you guys, we'll do this together like we did today, so we all understand it well. And yeah, we'll write these equations together on Friday. But yeah, that's about it. And I've already told you about this last class, that some of our metals have set charges, like group 1 metals have a +1 charge, but some of our transition metals have a specific charge, okay? We will always specify what the charge is, so you don't have to just make it up or think of it yourself. It will be given to you. And yeah, that's just a summary of key concepts. So guys, just before you go, I know it's already 2:30. I'm not going to keep you much longer. Just remember, on Wednesday, we have the practical activity assessment. You must come to class on time. On Wednesday, I believe I have you guys period 5 and 6. So you have to be here at 1:40 p.m. I will put the Zoom link up for that. I will be monitoring you through your Zoom and through EP. You must have cameras on. Fix your issues with your cameras and make sure that they're on. We are really being strict about cameras in assessments, okay? So if you don't have your cameras on or you're not cooperating, it will be reported to YLC coordinator. So you have to be making sure that you have your cameras on, okay? If you have any questions about anything we've done, please email me. And I want you guys to spend the rest of today finishing up your 3.5 worksheet. So whatever questions were left over, I want you to give those a go and to also revise the topics that we did today again. And let me know if you have any questions. And I'm just going to stop the recording here.